Okay, welcome to Let's Get to the Marks. Looking at the Combined Science Trilogy paper 2021. This is chemistry. It's paper one is higher. There's 7 questions in total. Let's get into it. This question is about the periodic table. Figure 1 shows part of Mendeleev's version of the periodic table. Here it is. Which group of elements had not been discovered when Mendeleev's version of the periodic table was published? So what we want to do here is have a quick look. What elements can you not see? So we can see we've got lithium, sodium, potassium. We've got some group 1 elements. We've got carbon and silicon over in group 4. We've got nitrogen and phosphorus from group 5. We've got oxygen, sulfur from group 6, fluorine and chlorine from group 7. And then over here, we might be expecting a certain group of elements. They're not there. We've got iron, cobalt, and nickel. We've got some metals. So which group of elements had not been discovered? Hopefully you know it. It's the noble gases. What I recommend you do is at the start of each question, you watch the walkthrough until I've got to the actual question, and then you pause the video, have a go at the question, and then unpause and check out the answer. You can either try to answer it in your head or you can answer on a scrap bit of paper with a pen. Let's go. Okay. Figure 2 represents different models of the atom. So we got one model here, A, another one, B, C, and D. 1.2. Which model represents the plum pudding model? It's 1 mark. Why don't you pause the video now, have a go, then unpause and check the answer. Okay, so which is the plum pudding model? Well, you will be forgiven if you went for B. It looks very similar to the plum pudding model. In fact, it is the plum pudding model. Why? Because it's a ball of positive charge. You see that big fat plus sign there. It's a ball of positive charge with negative electrons embedded within. You can say stuck within. Make sure you don't say a circle of positive charge. You won't get a mark for that if asked to describe it. It's a ball or a sphere of positive charge with electrons embedded within. Okay, the answer is B. Let's move on to the next question. 1.3, which model resulted from Chadwick's experimental work? Now, this is kind of a memory recall one. You either know it or you don't. Chadwick discovered the neutron. So based on that fact, that's not how you spell discovered, discovered. Okay. He discovered the neutron. Now, based on that fact, James Chadwick discovering the neutron, which one of these do you think is a model made that could only be made by the discovery of the neutron? Well, if we have a look, there's no neutrons, there's no nucleus in the plum pudding model. This is Dalton's model, which is just a solid ball. And then we have Niels Bohr, or sorry, Rutherford's model, the atomic model here, where we have protons in the middle and electrons orbiting in shells. And over here, once the discovery of the neutron was made, we have the neutrons in the nucleus. We can only have this model after the discovery of neutrons. So the answer is going to be A. Okay, let's move on to the next question. Potassium has different isotopes. This is question 1.4. What is meant by isotopes? You should refer to subatomic particles. It's worth 2 marks. Pause the video, have a go, write it down on scrap paper, unpause the video, check out the answer. Okay, hopefully you know isotopes are elements or atoms, I'm going to say, atoms of the same element with the same number of protons, but a different number of neutrons. Now, I know in some exam boards, they don't mind you saying that the isotopes are elements with the same mass number, but a different atomic number. AQA prefer you to be very specific and say that they have the same number of protons. Of course, that means you have the same atomic number and a different number of neutrons, which will result in a different mass number. But AQA are very clean and clear on you saying same number of protons, different number of neutrons. And that's the isotope definition. Okay, we're going down to 1.5, and it's a nice simple calculation. It's worth 3 marks, and it's the last part on question 1. Table 1 shows the mass numbers and the percentage abundance of two isotopes of potassium. So we have the mass number of the first isotope is 39, and there are 93.1% of all the potassiums in the world are 39 mass, and 6.9%, the remaining potassium in the world, have a mass of 41. What is the average mass? Now, obviously, if this was 50-50, the average mass between 39 and 41 would be 40. 39 plus 41 divided by 2 is 40. But here we have to take into account the abundance. So the relative atomic mass, the AR, which we are calculating here, calculate the relative atomic mass, is the average mass of the isotopes taking into account the abundance. Give your answer to one decimal place. We've got to calculate this to one decimal place. It's worth 3 marks, and you've got to know the equation. So here's the equation. So here's the equation that you need to know off by heart. You won't be given this one, and it is the AR or the RAM is equal to this sign, which is the sum of the mass of each isotope times its abundance. So 39 times 93.1 plus 41 times 6.9. The sum means you add them together, and you're going to divide that by the total abundance. In this case, that is 100%, and normally it will be 100%. So let's go ahead and do that. We want to do you might want to pause the video and have a go on a bit of paper. Make sure that you can actually do it. 39.31. You've got to bust that into your calculator in brackets. Otherwise, you're going to get all kinds of mistakes going on. And then plus 41 times 6.9. And then we're going to divide that by 100. And that is going to get us. Let's smash that in the calculator. 39.1 times 93. Oh, it's not 39.1, is it? It's 39 times 93.1 equals that, plus bracket 41 times 6.9 equals that, divided by 100 equals that, equals 39.138. So 39.138. And they want this to just one decimal place. Now, the 3 is less than 5, so we're going to leave this as 39.1 rather than rounding it up to 0.2. If it had been 39.14, or actually 39.15, we'd take it up, or 39.16, or 39.15, we'd take it up to 39.2, but actually it's 39.1, and that's going to get you your 3 marks like that. Okay, that's the end of question 1. Let's get into question 2. Acids react to produce salts. Universal indicator is added to water, and then nitric acid is added to the mixture. Give the color change when nitric acid is added to the mixture of universal indicator and water. So we have universal indicator with water. We've stuck an acid in there. What color does pH paper or universal indicator go when there's an acid? Well, first of all, we have to ask ourselves, what color would the universal indicator be in water? So what is the pH of water? Well, if it's pure water, its pH should be 7, and you should know the color of neutral of water is green. So that crosses out these two because we know it must start as green. And then they're saying they're adding nitric acid. If you add nitric acid, the pH is going to decrease because acids have a pH of 1 to 6. So which one of these colors represents a pH of 1 to 6? Nitric acid is a strong acid, so we're looking at it going green to red. Green to purple, would it be going alkali? The pH would be increasing, but nitric acid causes a decrease in pH, and it's going to either be 1 to 6. In this case, it's gone red. It's probably pH 1. There's nitric acid. Learn your pH colors. 2.2. What happens to the pH of water when nitric acid is added? So what happens to the actual pH of the water? Does the pH of the water decrease, stay the same, or increase? Well, we know that the pH of the water must actually decrease because we said it was starting at pH 7. And then if it went to become, well, if it turned red in color, that's pH 1. So it's decreased. What is the state symbol for nitric acid. In fact, it's not just nitric acid, by the way. Nitric acid, you don't need to know the formula off by heart, but it's NHO3. But whether I had nitric acid, hydrochloric acid, or sulfuric acid, and these are some of the very common acids that you need to know the formulas for, all of them will have the same state symbol, and it is AQ. And what's the reason? Well, you can only be an acid if you are in solution. And the reason, because you need to donate your hydrogen ions. You need to release hydrogen ions. That's what makes something an acid. So the state symbol for nitric acid is AQ. It's not liquid. It's not solid. Cool. That's going to get you. I'm up for that. I'm up for that. All right, let's move on to the next part of this question two. I'm ticking random bits of the page now. Okay. Zinc carbonate reacts with nitric acid. The word equation for the reaction is zinc carbonate plus nitric acid goes to zinc nitrate plus water and carbon dioxide. It tells us that zinc carbonate is white. It tells us that zinc nitrate is colorless. Give two observations that would be made when zinc carbonate is added to nitric acid until the zinc carbonate is in excess. So you've got to know what this word excess means in chemistry. Excess means when you have extra of zinc carbonate. And of course, once the zinc carbonate is in excess, once you add as much as you like of the zinc carbonate, eventually you're going to run out the nitric acid. So what are you going to be left visually seeing? Yes, you're going to see a colorless solution form, which is the zinc nitrate, but you're going to get white solid in a colorless solution. So that is one of the observations. So we can say white solid. If we want, we could say floating, but it might not be floating. If it's more dense than water, it will sink. White solid floating or in a colorless solution. So we know it's going to look like water, but with some chalk or some white solid floating in there. And that's going to be the zinc carbonate. And that's going to get us a mark. I reckon if you just said I'd see white solid, you'll get the mark too, but that's a little bit of further explanation. Now, what else here could you visually see? Can you visually see water? Well, if you've already got a colorless solution, how can you tell that water's been made? You can't tell water's been made with your eyes. That could be acid, could be anything that's colorless. Many, many different colorless compounds. So don't say, oh, I'd see water, because you can't tell if something is water by looking at it. But you will be able to tell with the formation of this. And why can you tell about carbon dioxide? It's a gas. And if you have water present or a solution present, what do you get to see? If you see a gas in a liquid or in a solution, you get to see bubbles, effervescence, or fizzing. So I'm going to say bubbles of CO2 gas. Again, would you know it's carbon dioxide? No, you'd know it's bubbles of gas is what you'd observe. So don't say really things that you can't tell by observation. They're going to say in the mark scheme, ignore the name of the gas. So if you say, oh, I could see carbon dioxide, they're going to say, well, no, you couldn't. You could see bubbles. You wouldn't know it's carbon dioxide unless you did the lime water test. Okay, let's move on. 2.5, the formula of a zinc ion is Zn2 plus. I'm going to make that a little bit bigger by writing it out for you guys. The formula of the nitrate ion is NO3 minus. What is the formula for zinc nitrate? So we've got some various formulas down here. What you need to do when working out formulas, if you know the charges of the ions, and normally we can find them by the group number, you have to know the nitrate ion, by the way, guys, off by heart. You need to know that NO3 minus, that's its charge. Zinc 2 plus, they're going to give you that. They're not going to expect you to know zinc, but any group 1, 2, or 3 metal, you should know. So like sodium, potassium, you know they're +1, magnesium, calcium, you can look them up in the periodic table, they're +2, aluminium, +3. So you can look up group 1, 2, and 3 metals and find out what their charge is by their group number. Zinc is in the transition metal area, in the middle of the periodic table. So you have to be given the charge for zinc. They don't expect you to know that off by heart. So in what ratio will they combine? Well, when ions combine to form a compound, they normally cancel out these electric charges. So in order to cancel out a 2 plus, I'm going to need 2 minuses. So I'm going to need 2 NO3 minuses to cancel out Zn2 plus. So we can do this. Zn NO3. Look at the problem now. If I write 2 here, it looks like 32. So I'm going to need brackets. Zn NO3 2. And that is this bad boy over here. Lovely jubbly. Let's put a little tick there, and now we'll move on. Okay, we've got a 6 marker here. This is a very, very common one in combined science. In the last 6 years, this has come up about 4, maybe 5 times even. So it's a really common one. I keep thinking, oh, they're not going to ask it this year. And every year I think that they ask this question. So acids react with insoluble metal oxides to produce salts. Plan a method to produce a pure, and the clue is in this. They will always say this. Plan a method to produce a pure, dry, that's key. I'd circle that, and I'd circle pure, dry sample of the salt. Now they've given us the name of the salt they want us to make, and it's copper chloride. And they've said use an acid and a metal oxide. Now, because they haven't given us the name of the acid or the name of the metal oxide, we can get 2 marks from naming the acid and the metal oxide. But if we mess that up, we can still get 5 out of 6 from the method. So even if you can't work out the name of the acid or the metal oxide, you can just say mix an acid and a metal oxide, and you'll only lose, if you get everything else right, you'll only lose 1 mark. But let's work it out. So, copper chloride is the name of the salt you want to make. Now, you're going to use a metal oxide, which is a base. And when you mix an acid and base, you make salt and water. So we're going to get copper chloride. Now, the acid that gives you chlorides, is it sulfuric? Is it hydrochloric? Or is it nitric acid? Well, it's going to be hydrochloric. That's how you get a chloride salt. So we're going to take hydrochloric acid, and that's going to get us a mark. And we're going to mix that with which base? Well, I need something that's going to give me the copper metal in my salt name. And so it's a metal oxide. So we're going to use copper oxide. And what happens is the copper from the base joins with the chlorine from the acid, and you get copper chloride. The hydrogen joins with the oxygen and forms water. Okay, let's move on, let's move on, let's move on. This is potentially, depending on the mark scheme, going to get you 2 marks for naming the reactants. But if you didn't know the names of the reactants, you could just say this, and I'm going to just hit the rest of it, like warm the acid with the metal oxide. Why do we warm it? It makes the reaction happen faster, so it doesn't take all day. So we warm the acid with the metal oxide. Then what I want to say is keep adding the metal oxide until it is in excess. So that means until we don't have any acid left and we just have metal oxide. Then we know we've used all the acid up. And guess what? They told us that this metal oxide was insoluble. So in theory, we're going to have salt, water, and acid. So no acid. Once it's in excess, all the acid has been used up, and we've just got the salt, that's the copper chloride. We've got the water, H2O, and then we have the excess metal oxide here. So I've now got my metal oxide, salt, and water. Now let's go to these keywords. Pure. We want to get rid of the metal oxide. We want to get rid of the water and just be left with the salt. And we need to dry it at the end. So let's explain how to do that. So the first step is to get rid of the solid excess, filter off the excess solid, or you can say metal oxide. Notice I'm not saying copper oxide because I've already mentioned it up there, and maybe potentially you didn't work out what the name was. You can still pick all the marks off. So keep adding it till it's in excess, filter off the excess. If you want, you can say with a funnel and filter paper just to be a bit extra. And then what I want to say, once we've filtered that off, it's going to the filtering process is going to look like this. You've got your funnel, got your beaker. Now I've just got salt and water left in there, and I've got rid of my excess. So I'm nearly pure. I'm nearly pure salt. I want to get rid of the water. How are we going to get rid of the water? Think about it. We're going to heat the solution to evaporate some of the water. What are you going to use? A Bunsen burner? No, if you can remember, use an electric water bath or electric heater. It means you can heat gently. And in fact, if I can remember that word gently, I'm going to say heat gently the solution. That doesn't make any sense. To evaporate some of the water. Use an electric heater. You get more control. Bunsen burner, you could spit all the salt and the water out. It might bubble and spill all out, and then you don't end up with your salt, and it could be dangerous. Okay, anyway, we're heating it gently. We've evaporated some. When you see some crystals. Now, back in the day, we used to have to say put a glass rod into the beaker to encourage crystallization, but we don't need to say that anymore. So when you see some crystals, take off the heat and leave to cool. This process, this is known as, and I want to get this word in because it's always on the mark scheme here when you're making salt in this fashion. We want to leave it to cool. That's known as crystallization. You can say leave it to crystallize. Same mark as saying crystallization, name of the process, or saying leave the solution somewhere cool to crystallize. And finally, I want to filter the crystals. Some people would say wash with distilled water, but I'm just going to say filter the crystals and dry with a paper towel. If you really wanted to be extra, you could say wash and then filter. Okay, so evaporate, crystallize, dry. So really, if you're really struggling, if that's too much info for you to get down and the exams are coming, I would say you just want to say mix acid with the metal oxide, right? Until the metal oxide's in excess, filter off, evaporate some water, leave it to crystallize, dry it with a paper towel, and look at how many I've underlined in pink there. 1, 2, 3, 4, 5. You're going to get 5 marks from that. Okay. Even if you didn't know the names, just by saying add the base or the metal oxide till it's in excess, filter it off, evaporate some water, leave it to crystallize, dry the crystals with a paper towel. Bang. That's going to get you 5 out of 6. But if you can say the other bits like naming these or giving extra details, you're going to be guaranteed 6 out of 6. Okay, we're looking at question 3. Questions about energy change. A student investigated the temperature change when a 10 gram of ammonium nitrate was added to 10 centimeter cubed of water. This is the method used. Measure the temperature of 100 centimeter cubed of water. Add 10 grams of ammonium nitrate. Stir once. Measure the temperature of the solution every minute for 7 minutes. Here's the apparatus. We've got a thermometer inside a glass beaker. We've got the ammonium nitrate and the water. And so what is the dependent variable of this investigation? That is the question to 3.1. And 3.2 is give 3 improvements to this investigation or to the investigation to make the results more accurate. And that's worth 3 marks. Give 3 improvements. So why don't you pause the video, have a go on a scrap bit of paper, then unpause and check out the walkthrough. All right, so first of all, the dependent variable is the thing you're going to change in the reaction. So what are they changing? This question is about energy change. A student investigated the temperature change when 10 grams of ammonium nitrate was added to 100 centimeter cubed of water. This is the method used. Measure the temperature of 100 centimeters of water, add 10 grams of ammonium nitrate, stir it once, measure the temperature of the solution every minute for 7 minutes. So really our dependent variable is the change in temperature. And that is, they tell us that is what they're investigating. That is what they're measuring. So it is the change in temperature. Woo. And the dependent variable is what you're actually recording with your equipment. Great, great, great. Now, the next part of the question was, say 3 things that could be done to improve it. Okay, so if they're measuring the temperature change here, what kind of beaker should it be in or container? Should it be glass? Well, glass is a reasonable conductor, and so a lot of the heat energy is going to be lost and not be read by this thermometer. So I'd say a polystyrene cup, which is a good insulator, maybe put a lid on the top to stop heat loss. All of those are going to make it more accurate. What else? What else? What else? Measure the temperature of 100 centimeter cubed of water, add 10 grams of ammonium nitrate, stir once, keep the same surface area, so powdered ammonium nitrate, measure the temperature of the water every session for how many times are you going to stir it? Because it says stir once. You could stir more times. Um, use let's think. If we use a larger mass of ammonium nitrate, we're going to get a bigger temperature change. And a bigger temperature change is going to mean a smaller amount of error. So if you think about it, if your error is, if you have a 1% error and you're measuring, the temperature change is 10 degrees, well, 1% of that is wrong. But if the temperature change is 100 degrees, then it's only 1% of that that's wrong. So you get a smaller amount of error. Even if the error is the same size, you get a smaller amount when you have bigger measurements. So using more ammonium nitrate would give us a bigger temperature change and mean there's less error in the results. A more accurate balance. Instead of using an analog thermometer like this, where it's hard to measure, we could use a temperature probe or a digital thermometer, which actually gives us a quantitative value. So those would all be things. So I'm going to put 3 answers here. And my best 3 of the ones we've discussed would be polystyrene cup and a lid to reduce heat loss. So using an insulator is going to reduce heat loss. We could also say, whoopsie, what's going on there? What's happening there? We could also say repeat 3 times, remove anomalies. This is always a nice one, and calculate a mean. So when you repeat, you're able to spot anomalies and remove them, which is going to make your results more accurate because they won't have an anomaly, and you can calculate a mean. You're going to get closer to the true value. Okay, and then if we use a larger amount of ammonium nitrate, why is that going to improve it? You will get a larger temperature change. So you're going to get a bigger change in the temperature. Therefore, a smaller percentage error. So when you're measuring bigger amounts, it's more accurate. Okay. Here's some results. We've got figure 3. We've got, the question is, explain the results for 4 marks. So what you want to look at here is we've got a pattern as temperature, as the time goes across or increases, as time increases, temperature decreases. So we've got a section of the results to talk about here. And this is going to get us some marks and explain why it decreases. And then from this point to this point, we have an increase. So we've really got 2 sections of the graph to talk about, and it's 4 marks. So we're really going to get 2 marks for talking about that, and then 2 marks for describing and talking about that. So what I would do is, first of all, I'd describe what's happening here. So from 0 to 1.5 minutes, from 0 to 1.5 minutes, the temperature is decreasing. And why is that? Well, ammonium nitrate is dissolving, and this is an endothermic process. That means energy is being taken in from the surroundings, and that is why we're getting a decrease in temp. And that describes this part of the graph here. Now we're going to get 2 marks for what's going on here between 1.5 and 7. So between 1.5 mins and 7 minutes, the temperature slowly increases at a constant rate, whatever. But that is going to get us a mark for saying the temperature increases, okay, from 1.5 to 7. And why is that? That's because energy is being released to the surroundings. So we can say energy is being released, can't spell it, released to the surroundings. So you're really just explaining why the temperature goes up. Temperature will go up whenever energy is being released overall to the surroundings. Temperature will go down whenever energy is being absorbed from the surroundings. Remember, the temperature, the thermometer is measuring the temperature of the surroundings. So there's our 4 marks. Okay, 3.4, draw a reaction profile for an exothermic reaction. You should label the energy of the reactants and products, the activation energy, and the overall energy change. So this is for an exothermic reaction. This is the most common reaction, so know this one off by heart. You should also learn how to draw the endothermic, but it doesn't come up as often. That doesn't mean it won't come up for you, but I'm just telling you the facts that the exothermic reaction has come up like um, say 7 out of 8 of these questions have been exothermic, and there's only been like one draw an endothermic. So there we go. So reactants, that doesn't mean when you do the exam, it won't be the endothermic one. So reactants, products. So if you've drawn your reactants higher than the products, that's 1 out of those 4 marks. Your next stage is to draw a kind of camel's hump going up, then down, and then a dotted line across here. And this here with an arrow going up, this is the activation energy. So I'm going to just write AE, activation energy. And that is another mark for labeling the activation energy. Now, the next thing that we want to do is draw an arrow for the overall energy change. And the overall energy change is found between this dotted line and here. So this is my overall energy change. It's exothermic. So yeah, that's the overall energy change. So correctly labeling and drawing this arrow is going to get you another 2 marks. So arrow going down and labeling it overall energy change. I mean, yeah, there we go. 4 marks. Lovely jubbly. Carbon can exist in a number of different structures. This is question 4. 4.1. The first fullerene to be discovered was Buckminster fullerene. What is the formula of Buckminster fullerene? Tick one box. It could be C40, C50, C60, C70. It's worth 1 mark. Why don't you have a go? Okay. The answer here is C60. So they are spherical structures. Buckminster fullerene is a ball, and it was the first type of fullerene, which is a group of allotropes of carbon that were discovered. And this Buckminster fullerene was made of alternating hexagon and pentagon carbon rings in a formula or in a shape that contains 60 carbon atoms in a sphere. Don't get confused and think that this is a giant covalent structure because it has 60 atoms. 60 atoms is hardly anything. Just one tiny particle of diamond would have trillions of carbon atoms in it. So this is still a simple molecular molecule, hence why fullerenes are good lubricants. Right, let's move on. Graphite is a form of carbon. Explain why graphite conducts electricity. So when you're asked if something conducts electricity, graphite or metals, the first mark is the same. It contains delocalized electrons. Now, bit that probably people don't get for the second mark does depend on your exam board, but for AQA, they like you to say which can carry charge through the structure. And sometimes you might need to say, so this is a 2 marker. It contains delocalized electrons, which can carry charge through the structure. Sometimes if it's a 3 marker and they're asking you how the structure of graphite allows it to conduct electricity, yes, it contains delocalized electrons. Yes, they carry the charge through the structure, but there is an extra mark if it's a 3 marker, and that is to say that each carbon atom is only bonded to 3 others in graphite, which means they have 1 electron that is unbonded that forms the delocalized electrons. So it's just saying where the delocalized electrons come from, and they come from the fact that graphite only has 3 bonds for each carbon atom. If you compare that to diamond, which has 4 bonds for each carbon atom, there are no free delocalized electrons in diamond. All right, let's move on. It would help if I don't just randomly put ticks on the page. Steel is an alloy of iron and carbon. 4.3, explain why steel is harder than iron. So it's an alloy of iron and carbon. So pure iron, or it's to draw pure iron is made of just iron atoms in layers, which can slide, and that's why pure iron is soft. However, when we create an alloy, we use different sized atoms. So these black ones here are my carbon atoms. And what this does is this disrupts the layers, changes the shape, deforms the layers, you can say if you prefer, and this means they can't slide and it makes them harder. So what do we need to know? Like this is for any alloy. So this is in the context of steel, but they could tell you you have alloy X and it's harder than the pure metal Y. Why is alloy X harder? You would always use the same answer just in the context. So it is alloys contain different sized elements. If you wanted to put it in the context of this question, you would say steel is made of iron and carbon and not just iron alone. So alloys contain different sized elements. This deforms the layers, or you can say distorts the layers if you prefer the word distorts. You can just say disrupts the shape of the layers. So disrupts is another good word. Lots of words beginning with D there. This deforms the layers or distorts um, the layers or the shape of the layers. Um, the layers cannot slide. So it stops the layers sliding. There's your 3 marks. And of course, this makes alloys stronger. Now you could be prepared. You should quickly go over in your head. How would you answer this question if it said, why is iron softer than steel? And you wanted to answer it in the opposite way. You would just say iron only contains one element, which is iron atoms. They're the same size. It's arranged in layers. The layers can slide. So you've got to be able to, whenever you're doing these questions, kind of test yourself on similar questions, and that would get you the 3 marks. Iron is alloyed with carbon and other metals to make stainless steel. A stainless steel fork contains 71.92% iron. Table 2 shows the mass of each element in the fork. So we have iron, mass in grams, carbon 0.05, chromium 10.44, and nickel 5.80. Calculate the mass of iron X in the fork. Okay, I'm going to go through the answers. So hopefully you had a go at this yourself. Calculate the mass of X in the fork. First thing we want to do is say, okay, well, if iron is equal to 71.92%, then all of these other elements, what is their percentage? Well, we're going to do 100 minus 71.92. We're going to find out that all of these other elements equal 28.08%. That's how much all these other elements are equal to in a percentage terms. What's their mass in grams of these other elements? So let's go 10.44. Let's add that in our calculator to 5.80 and then add that to 0.05. And what we're going to find out is that 28.08% of this compound or alloy, sorry, is equal to 16.29 grams. So now I know how much 28.08% is. Let's find out what 1% is. And I can do that by going 16.29 grams over 28.08%. And that's going to tell me exactly what 1% equals. And so 1% is equal to 0.58. Well, I shouldn't really put it that, but yeah, that's what 1% is equal to, right? It's equal to 0.58 grams. So what I can do now, if I want to find out how heavy the iron is, I've just got to do 71.92 times 0.58, and that is going to give me the mass of 71.92%, which is 41.72 grams. And there we go. That's your final answer. What do you get the marks for? You get the marks for working out the percentage 28.08 of the remaining elements. You get the marks for adding up the mass and working out that 28.08 is equal to 16.92 grams. Then you just got to find out how heavy or what the mass of 1% is, which was 0.58, and then 0.58 times 71.92 is your 4th mark. Okay, question 5. This question is about electrolysis of aqueous solutions. Hydrogen gas and chlorine gas are produced when sodium chloride solution is electrolyzed. Hydrogen ions are attracted to the negative electrode. The half equation at the reaction at the negative electrode is 2 hydrogen ions plus 2 electrons becomes hydrogen gas. What type of reaction happens at the negative electrode? Give a reason for your answer, and it's 2 marks. So when we're talking about electrolysis and electrodes, we're talking about redox reactions. And hopefully when you're dealing with redox reactions, you remember oil rig. And what does oil rig stand for? Well, it stands for oxidation is loss of electrons, and the rig bit stands for reduction is gain of electrons. So if you pick up electrons, you're getting reduced. If you lose electrons, you're being oxidized. Well, if we look here, the hydrogen ions are gaining, they're picking up electrons to become hydrogen. So this is reduction. Okay, they're gaining electrons, and that is the reason. Now, so we are going to say this reaction is a reduction reaction, type of reaction, reduction, because electrons are gained, but I'm going to be more specific because hydrogen ions gain an electron each. And we could say 2 hydrogen ions gain 2 electrons, but they basically, each hydrogen ion gains an electron, and that is why it's a reduction reaction. Zinging down to 5.2, chloride ions are attracted to the positive electrode. Complete the half equation for the production of chlorine gas. So this is happening at the positive electrode. Chloride ions are negative, so they're attracted to it. Guess what they're going to do? The hydrogen ions were reduced. These are going to be oxidized. They're going to lose electrons. So we've got a chlorine ion is going to become chlorine atoms. But chlorine actually doesn't exist as single atoms. It exists as diatomic molecules. So it's a diatomic element, always 2 atoms joined together to make this molecule, okay, Cl2. So are all the other halogens. That means I need 2 chloride ions to balance it up. And each one of those chloride ions is going to lose this negative charge, which we now know is an electron. So each chlorine atom or ion has to lose one of these electrons to become chlorine gas. So we've got 2 chloride ions go to a chlorine molecule, and it gives away 2 electrons. And that is oxidation if you were being asked. And people get confused. Why is it oxidation if you've got a plus sign with electrons? Surely that's gaining electrons. When you're on the right-hand side, it's showing you that the electrons are lost. You've got chlorine and 2 electrons coming out. Okay. That bit's always confusing for people. 5.3, hydrogen gas and oxygen gas are produced when sodium sulfate solution is electrolyzed. Explain how oxygen gas is produced in the electrolysis of sodium sulfate solution, and this is worth 4 marks. So what I'm going to go through here, there's some rules to electrolysis, but essentially, excusez-moi, you have a positive electrode and a negative electrode, and we have sodium sulfate solution. We've got some ions, 4 ions in all solutions. So, well, yeah, in the ones you'll deal with in GCSE. So we've got sodium ions, and then we've got sulfate ions. Now the sulfate ions are SO42 minus, so positive ion, negative ion. But when you're dealing with a solution, that's AQ, you're also AQ, which means aqueous, contains hydrogen ions and hydroxide ions. So the question is, you've always got a battle, like which of the positive ions will go to the negative electrode? Is it going to be the sodium or is it going to be the hydrogen? And it's always the one that's less reactive. It's any metal less reactive than hydrogen ions, and sodium ions are more reactive, or sodium is more reactive than hydrogen. So sodium stays in the solution and hydrogen comes off. But we're not focused on that. They're asking us, how is oxygen gas produced? Well, you've got a choice of sulfate ions or hydroxide ions. Now, the sulfate ions never come off in electrolysis. It's always going to be the hydroxide ions. The only time hydroxide ions don't come off is if you have a halide, which is a halogen, a group 7 element present. But in this situation, there are no halogens. So the hydroxide ion goes to the positive electrode and it forms oxygen gas, and it forms water as well. And it releases its negative charge, the electrons, into the positive electrode. So there's a whole number of things that we can work with this. So I'm going to write the equation out. You get 3 marks just from the balanced equation. But why does it happen? I would just say hydroxide ions are negative. They are attracted to the positive electrode. So the hydroxide ions are negative. They're attracted to the positive electrode. Why? Because its opposites attract. What happens to them? Do they get oxidized or reduced? Well, when we're at the positive electrode, we're going to lose electrons to that positive electrode. So they get oxidized. They lose electrons to form water and oxygen gas. So that's kind of an explanation of what is going on. The hydroxide ions go to the positive electrode, 1 mark. Because they're negative and the electrode is positive, that might be 2 marks. They get oxidized, they lose electrons to form water and oxygen gas. Let me show you the equation for this. So it's hydroxide ions we start with, then we go to oxygen gas and water. And of course, I need to get rid of that negative charge. So I'm going to put an electron over here. And this is the hardest half equation. You have to memorize this off by heart, or you can just learn how to work it out. So I've got 1, 2, 3 oxygen atoms over here, and I've got 2 hydrogens. So it's going to be a bit awkward. I want to balance this up and make even numbers. So I'm going to have 2 oxygens there and 2 there. That's 4 oxygens. So I'm going to need to put a 4 here, and the 4 oxygens there. 2 there, 2 there, that's 4 oxygens. I've got 2 times H2, I've got 4 H's there. We're all beautifully balanced. The only thing is this big 4 means I've got 4 times minus as well. So I need 4 electrons over here. And that's the equation that essentially is happening. And that is how oxygen gas is produced by electrolysis of sodium sulfate solution. Okay, metal oxides. Where am I? Where am I? Where am I? Here I am. Right. Question 6. Metal oxides are produced when metals are heated in air. A student investigated the change in mass when 0.12 grams of magnesium was heated in air. So they've heated a tiny amount of magnesium there. Figure 5 shows the apparatus. We've got a lid on a crucible. Normally these are made out of some sort of white ceramic or porcelain. You've got some magnesium ribbon, it looks like, curled up. We've got a tripod. When you draw the tripod, you can never see the third leg, but there we go. And you've got the heat going up here, heating this, and we have a balance that's going to 0.00 grams. So it's going to 2 decimal places. The student measured the mass of the magnesium oxide produced. 0.12 gram of magnesium reacted to produce 0.20 grams of magnesium oxide. Calculate the number of moles of oxygen that reacted. Relative formula mass is 0.16. So we want to work out how many moles of oxygen. Losing my skills here. Right, we've got mass. We've been given 2 masses. We've been given the AR or MR, however you like to think of it. And that means, boom, you've been asked to calculate moles. So number of moles, I use an M for number of moles. And so that comes to mass over mR times moles, the most common equation you're going to use in GCSE chemistry. Learn it off by heart. It's probably the most common equation you use in A-level chemistry as well. So mass over mR times moles. mR can be AR as well. Let's get into it. So first of all, we're given 2 masses. What do you think you've got to do here? Well, we're going to take 0.20. We're going to minus 0.12, and that is going to give us 0.08 grams of oxygen. And that is how much oxygen we've actually got. Okay, because it's magnesium oxide. So that's MgO, just for you, those of you that, and that's Mg. So we're taking the Mg away from the MgO, and we're left with the O, and that is our mass of oxygen, 0.08. Now I want to find out the moles of oxygen. Here's the point where people will make a mistake, because you'll get 1 mark for this, but here's the tricky bit. You can go 1 or 2 ways, and one of them is wrong. So we're going to go 0.08. We're going to consult our equation and say, I want moles, which is N. I need to divide it by the MR or the AR. And so some people are going to divide it by 16, and some are going to say, well, 32. Well, oxygen has the formula O2, so I need to times that by 2 and do 32. It didn't ask me for how many moles of oxygen atoms. If it asked me for how many moles of oxygen atoms, I'd divide it by 16, but it said how many moles of oxygen gas, O2. So I need to do 16 times 2 is 32, so 0.08 divided by 32, and this is going to give me 0.0025 moles. Now, let's say you messed up and you divided by 16. The fact that you did mass over the AR, you'll probably still get 2 out of 3 marks for that. And you'll definitely have picked up a mark for working out the mass, and probably still for doing mass over MR or AR, you'll still get a mark, but you'll get the wrong amount of moles. Okay, let's zing on. Enough of my wiffle waffle. 6.2. The student repeated the experiment without a lid on the crucible. Suggest why the mass of the magnesium oxide produced would be different without the lid. So if we didn't have the lid, we have some issues. When you're heating at that high temperature, although magnesium oxides are solid, if you don't have the lid on, some of that solid may have escaped. So that's why we've got less. Some of it may have vaporized and escaped if you've heated it high enough. So the mass would be less, as some MgO would have escaped without the lid. Now that's because some of it may have vaporized. You get a white smoke when you heat magnesium, and that is vapor of magnesium oxide. Normally it's a white solid. If you keep the lid on, it's going to go to the top, it's going to cool down, it's going to drop back down, and you're going to have that mass inside the crucible. It won't escape. So even if it's vaporized, it still has the same mass and it won't be able to get out. Once you take the lid off, any magnesium oxide vapor, even though the majority will be solid, any magnesium oxide vapor will escape. So 2 marks here are for say the mass would be less. So if you said it would be more or less, more would be wrong, it would be less, and it's because some would have escaped. Okay. Right, let's zing down. Copper, 3 marker. Ooh, 6.3. Copper reacts with oxygen to produce copper oxide. 63.5 grams of copper produces 79.5 grams of copper oxide. Calculate the mass of copper oxide produced when 0.50 grams of copper reacts with oxygen. Give your answer to 3 significant figures. Ooh, right, let's go. So we got copper reacting to form copper oxide. I mean, it all depends, really. Did they give us the equation up above? I'm writing the equation out, but they may have actually given us the equation. Let's check it out. Excusez-moi. No equation. Okay, that's cool. We won't need the equation because it's going to be 1-to-1 with copper to the copper oxide in this situation. So we're going to go 63.5 grams makes that. Calculate the mass of copper oxide produced when 0.5 grams reacts with oxygen. Okay, so this is more of a ratio thing. So I can do 79.5 grams of copper oxide, divide that by 63.3, divide that by the copper, and then times by 0.5, and you are going to get 0.62598. Now, because the 5 is bigger than the 2, or I should say, take that back, we're not going to 2, we're going to 3 significant figures. So the 9 is bigger than 4. We're going to round that up to 0. We don't count the 0 in the significant figures, 0.626. We're going to round up because the 9 is larger than, if anything over 4 on this 4th significant number, we round that up to give us our 3 significant numbers. Anyway, let's move on. 6.4, iron reacts with oxygen to produce iron oxide. 0.15 moles of iron reacts with 0.010 moles of oxygen gas. Determine the formula of the iron oxide produced and the balanced symbol equation for the reaction. Okay, there's more than one way to do this. Let's get into it. Okay, you might want to pause the video, have a go at this one on a scrap bit of paper. This one's actually a tricky one, and if you can get just a couple of marks, you've done pretty good because it's quite a tricky little number. So what we have here is we have 0.015 moles of iron, formula Fe, and we have 0.010 moles of oxygen gas. Here's the mistake some people will make. They're going to write O there for oxygen, but once again, oxygen gas, it's O2. So our ratio is 1.5 to 1. Obviously, we want to make that whole number. So let's times them both by 2. So we're going to work out with Fe is 3 in a ratio to my oxygen gas of 2. Here's the mistake. People will now go to write the formula, and they'll write the formula like this: Fe2O3, because they've worked out the ratio was 1.5 to 1. They've multiplied it by 2, which is beautiful, and they've worked out the formula of iron to oxygen is Fe3 to O2, and that's given them a mark. Okay, but then they come to write the overall formula and they do that, and that is wrong because, of course, each oxygen molecule has 2 atoms. So the actual ratio of iron atoms to oxygen atoms is 3 to 4. So what that means, because I've got to do 2 times 2 here. So we could write correctly, the ratio should be 3 iron atoms to 4 oxygen, and that would be the correct formula. So that's going to give you where's my tick? There we go. There's my tick. And that was going to give you another mark there. Now, you possibly get a mark. Well, I don't think you get a mark for that. We now need to write the equation and balance it because it says balance. So we're going to get a mark for the equation and 1 mark for balancing, and that's going to make the total of 4 marks. So if I'm making iron oxide, I need to start with iron, Fe. I need to add it to oxygen. Remember, oxygen's diatomic. It doesn't exist as oxygen atoms, just O. So it's going to be Fe plus O2. And now we got the correct formula, Fe3O. They will error carried forward here. If you got the wrong formula and you wrote Fe2O3, I think you'll still gain at least 1 out the 2 marks for the equation if you do the equation right, because you'll get some error carried forward. But this is the correct way to do it. We've made Fe3O4. So what do I need to do? I'm going to need 3 ions to make the Fe3, and I need 2 O2s. I need a big coefficient 2 here to go 2 times O2 to make the 4 oxygens. And Bob's your uncle, Fanny's your aunt. 1 mark for the correct equation, 1 mark for balancing it all correctly. Total of 4 marks. Lovely bubbly. Should be lovely jubbly, but we like to get a bit different. Question 7, methane, ethane, propane, butane. Ooh. All react with oxygen to produce carbon dioxide and water. Suggest why a mixture of methane and oxygen does not react at room temperature. Answer in terms of particles. So I hope you know that methane, ethane, propane, and butane all end with the letters A and E. These are all hydrocarbons and they're all alkanes. What is the reason why 2 chemicals might not react? We've got to think in terms of our collision theory. So this is about collision theory. So we're going to say the particles collide. So if you have methane in the room with you now, well, you'll know, because when you turn on your Bunsen burner at school and you don't put a light to it, the gas doesn't suddenly react. You don't get a flame unless you put a light or a match or a lit splint. When you light your Bunsen burner at school, you have to get a lit splint, hold it over the Bunsen burner, and then the methane, propane, etc., the mixture of gases in that Bunsen burner will react with the oxygen in the air. And once you've applied that, what are you giving it? You're giving it activation energy. Without the activation energy, the particles do not have enough kinetic energy. So when they collide, they don't collide successfully. So we just need to say the particles collide, but but do not have enough energy to overcome the activation energy. So they do not react. Same thing with petrol. In the movies, you always see car crashes and cars explode into flames like a bomb's gone off. But actually, petrol doesn't react instantly with oxygen. You need activation energy. You need some sort of flame, and you need the right amount of particles for them to collide with enough energy to get a successful collision. So you can say collisions are not successful, if you like to say that. All of these are good points to make. The particles collide, but they don't have enough energy, so the collisions are not successful. That would get you 2 marks. Or you could come out with the funky bit and say they don't have enough energy greater, they don't have energy greater than the activation energy, or they don't have enough energy to overcome the activation energy. You get the idea. Anyway, it's 2 marks, but I've given 3 ticks. But there you go. I'm being generous. Table 7.2, no, not table 7.2, question 7.2, table 3 shows the energy released when methane, ethane, propane react with oxygen to produce carbon dioxide and water. So we can see CH4 gives out 680, C2H6 gives out 1160, and C3H8 gives out 1640. Predict the energy released when butane reacts with oxygen to produce carbon dioxide and water. Well, this is just testing your ability to predict patterns in chemistry, which you need to know for science anyway. So there's the formula, C4H10. What factor are we kind of going up by? It looks like we're sort of going up by what, 30%, 40%, 60%, sort of a 60% increase, something like that. So look, we've gone from that to that. Yeah, maybe 50, 60%. So I think if you added about 700 to this, 700 or 800 to this, you're going to get the right marks, and they're going to have a range. So you're going to get a range of answers that they will accept. There is a more accurate way to do it. And of course, we can just find out how much energy is given off for each carbon atom in the chain. So as we're just making a prediction, it's not going to be perfect, but you just will give something. They'll accept a range here. So you're just following patterns, and you know it's going to increase, but obviously don't put 4,000, don't put 3,000. It's not doubling every time. So there we go. Okay. Let's go down a bit. Okay, so we have this question here. It says propane reacts with oxygen to produce carbon dioxide and water. We can see it there. The displayed equation for the reaction is here, given all the displayed bonds. Lovely jubbly. Let's move down a bit because I want to get a bit more space. So we've got propane plus 5 oxygens goes to 3 carbon dioxide and 4 waters. The reaction's exothermic, giving out energy. In the reaction, the energy released from forming new bonds is 1,640 kg per mole greater than the energy needed for breaking bonds. That essentially tells me that the energy change for the reaction is minus 1,640. And they told me it's exothermic. Whoopsie. So I know that it's going to be negative sign. And that is the overall energy change. Now, the equation for this, if you've done some of these in other ones, is generally we're just going to do reactants, and we're going to add up all the energy in the reactants. We're going to put a minus sign in the middle where the arrow is. I like to put a minus sign there. And then we're going to write all the energy of the products. Now, this is a harder one because it's worth 5 fat marks, and that is going to equal the energy change. Now, they've given us the energy change, and we've got all the numbers to work out the reactants and products, but we haven't got the CC bond. We don't have this, which is 2cc. We don't have 2cc, so that's the only thing we can't work out, which is 2cc. We can add up everything else, and then we're going to rearrange it, and let's have a go at that now. So what I'm going to do is you're going to get 1 mark for writing down the reactants. Forget about the 2cc, but for writing all the CH bonds and the 5 O's. You're going to get 1 mark for writing all the products. So adding up all of these numbers, multiplying by this, and adding up those numbers, you're going to get 1 mark for that. Then you're going to get 1 mark for rearranging and another couple of marks for solving. Okay, let's do it. So I've got how many CH bonds here? 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. So I want to do 8 times 410 and write that down. You might even pick up the odd mark for some of your working out like that. That is 3,280, but I'm not done yet. I need to add that to 5 oxygen doubles. Each oxygen double is worth 500. So I'm going to do 5 times 500, whatever, that's 2,500. So I'm going to add 2,500 to that. And I get a total. Here's your first mark on the board for the reactants. I've got a total of 5,780. But don't forget, we got these 2cc bonds. So I'm going to put plus 2cc. I'm going to write my minus, and now I'm going to work out all the products so I can get that number going. Okay, so for the products, I've got 2 COs here, which is 740 times 2, but there's a big 3. So I want to do 3 times 2 times 740. I know what you're saying. Why don't I just do 6 times 740? You can do. Right, so 6 times 740, what does that give me? That gives me 4,000 440. Lovely. That's all the energy given out from carbon dioxide. I now need to do the same thing here. I've got two OHs, which is 460. But of course, I've got four lots, so I could do 8 times 460, or I could do 2 times, 4 times, however you want to do it. So I'm just going to do 8 times 460. And if you're wondering why is it 8 times 460, I've got a 4 here. That stands for 4 times, but there's 2 lots of them. So I'm doing 4 times 2 times 460, which is the same as saying 8 times. So anyway, 8 times 460. So I'm going to go plus 8 times 460. And I'm going to whack those together. I'm going to add those together, and I'm going to get a total on this side of 8120. So picked up a couple of marks here. You're going to get 2 marks out the 5. One for coming up with 5780 anywhere in your working, plus 2x or plus 2cc. And then we're going to get a mark for coming up with minus 8120. And then all we need to do, we're going to get one more mark, can't speak, for showing that that equals minus 1640. So now what I need to do is solve this equation. You get one more mark for working out that it's minus 1640. They didn't tell us it was minus 1640. They told us the energy released was greater than the energy taken in. Well, that basically means the energy change was minus 1640. So interpreting that will get you 3 fat marks. The other 2 marks are for solving this. So what I want to do, first of all, there's a couple of things you could do. I could add 8120 to both sides. If I add 8120 to both sides, let's go ahead and do that now. So my first step would be like add 8120 to both sides. Whoopsie, to both sides. And what you're going to do then, we're going to end up with 5780 plus 2 cc, right, is equal to, I've got minus 1640. I'm going to add 8120, and that's going to give me is equal to 9760. So what I needed to do is 8120 add minus 1640. That is totally different. That equals, I don't know what stupid number I came up with there. You always got to double check on your calculator. That didn't make sense. How can I add 8120 to minus 1640 and get 9? That means somewhere in my calculator I haven't put the minus sign. So that is a lot better. So I've got 5780 plus 2c equals 6480. Now all I need to do is subtract 5780 from each side, and so that I can stop waffling, minus 5780 each side. And now I'm going to come down here for this, guys, because I'm running out of room up here. So I'm going to come down here. If I take away 5780 from each side, I'm going to be left with 2cc equals 6480 minus 5780. And that is going to give me 700. Now I want to find out what 1cc equals. So I divide both sides by 2. And if I divide both sides by 2, I'm going to get like 700 divided by 2 is going to give me 350. And that is my kind of final answer, right? So bosh, bang, 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 5 marks. Lovely. Okay. Superbulous. I hope that helped, guys. Don't forget, I have got loads more of these videos. I'm going to be doing all of the combined science videos before the exam. So, check out the other videos. That's what I'd say. Don't forget, sharing's caring. Hit the like, punch up the bell. Let's get to the marks and smash those exams.
You're still here? It's over.